Okay. Previously, we talked about the mathematical modeling and the spectrum for AM, DSP, and AM, DSP, SC modulation, right? So now we are discussing some practical issues. How we're going to do the modulation technically, and how we're going to do the demodulation. Okay. So from an expression of AM, DSP, and AM, DSP, SC, it's clear that we definitely need a multiplier, right? Because you see, here we can see a multiplication of the carrier signal with the envelope. Here we can see the message and multiply with the carrier. So we definitely need a multiplier. Okay. All those modulator with a multiplier is called product modulator. Means that actually there are some other ways to do the modulation. You will see, actually you will see from practice question. Okay. Of course, all those product modulator or other nonlinear modulator are all called modulator. Basically, it means that those modulators try to produce modulated signal. Okay. In other words, those modulators must receive two input. One is the carrier, the other one is a message. Okay. So, for example, for AM DSP, okay, it's simply just these two. Okay, you receive message signal, also carrier signal. Okay, so according to the modulation and mathematical modeling, is a carrier. This one can be written as a carrier signal multiply add with second term here. The second term actually is a multiplication of message with the carrier signal. Of course, scaled by mu. Mu because it's constant. It always can be implemented by an amplifier. Right? So the scaled version of message coming multiplied with the carrier signal. At this point, the signal should be mu xt times the carrier, right? Second term over here. Then sum together with the carrier signal. First term over here. So this will produce the AM DSP modulated signal. Okay. Of course. If you just use this two notation, it looks very simple. Okay, multiplier, adder. Of course, this adder is an analog adder. It's not analog adder. All right. If you look at your lab menu for your lab tree, you will see that actually even for this analog adder, it's not so straightforward. You at least need two op-amps to implement this analog adder. Analog adder. All right. So don't mention about this multiplier. Multiplier itself is a three-port component. That means there are two input port, one output port for multiplier. Generally, it's very hard to implement it. Why? Because multiplier, in most of the cases, is a non-linear element. Means that at this point, you will produce a product of these two inputs plus some other production component. So practically, if you're looking at a practical multiplier, you need adding some filter to reject those high frequency harmonics. Only keep the product term at this point. Fortunately, in this lab, you don't need to worry about it. Because in the lab, this one's supposed to be ideal multiplier. Okay, but in the working place, every time when you use a multiplier, you need to tell yourself, you're going to expect some unexpected component at this point. How to remove this component? You need to multiply some filter. Okay. Whereas in the lab, you don't need to do that because the lab gives you an idea multiplier. But you need to work out the analog adder. Okay. There's an appendix for your lab tree show you how you can implement an analog adder. Okay. So please go through this appendix before you do your lab tree. All right. Don't ask me how to implement this adder. You cannot find anyone from the library at all. There's no analog adder library from the software. You need to implement yourself. Okay. All right. Well, for AM, DSP, SC is simple because it's just two multiplication terms. Okay. message and carry. Okay, the output will give you the AM DSP SC modulated signal. Okay, looks very good, right? But same thing, this multiplier, although mathematically we just use this notation, but it's not very straightforward. Basically, if you want to implement the multiplier, okay, you need to know this. All right, demodulation. Demodulation, we have mentioned about the envelope detector, right? Remember, we have an envelope detector for AM DSP with mu less or equal to 1, right? At this part, we are not talking about those envelope detector. We are talking about coherent detector or coherent demodulator. Why we call it coherent? It's because at the demodulator side, that means the receiver side, right? We assume we have an oscillator. This local oscillator is called local oscillator, right? That's why we have an ALO, local oscillator, which has the same frequency and same phase as the transmitter side. Okay, there are two independent oscillators. Somehow, by signal processing technology, we can achieve this such that the receiver side local oscillator has the same frequency and same phase as the transmitter oscillator. Since the transmitter receiver are far apart, they are far away, right? So how to achieve this? How to achieve this itself is a very challenging task. Even today, in the research, this one is not achieved perfectly. More or less, they still got some residue errors. So in this section, we assume that we have a genie to help us such that, I use a dotted line here, all right? We have a genie to help us such that at the receiver, we can perfect recovery the local oscillator, which has the same frequency and same phase as the transmitter oscillator. All right. To achieve this, in communication or in research area, it's called synchronization. Synchronization. Okay. Those detector or demodulator with this local oscillator is called coherent detector or coherent demodulator, or sometimes it's also called synchronous detector. All right. So with the help of this local oscillator, I need another multiplier. So the modulated signal, okay, modulated signal, no matter it's AM DSP SC or AM DSP, come in, okay, the receiver antenna, detect this signal. This signal pass through another multiplier together with the local oscillator signal, which is same frequency and phase as the transmitter carrier. All right. So it produces a signal YT. Okay, so what's the expression for this YT? For example, AM DSP signal. What's the expression for YT? Assume XCT is the same as the signal from the transmitter antenna. So what is the expression for YT? For AM DSP. Can you ready? Can you ready it up? What is the expression for YT at this point? Let's assume the carrier signal is AC times cosine omega CT, and the message signal is XT. Okay, so and the modulation index is mu. Okay, so in that sense, what is XCT? XCT is supposed to be AC times bracket 1 plus mu times XT, right? Then bracket times cosine omega CT. Am I right? Now you multiply with ALO cosine omega CT. What do you have? What you have is AC times ALO bracket 1 plus mu XT times cosine square omega CT. Am I right? In XCT, you already have a cosine omega CT, right? This is modulated signal, AM DSP modulated signal. Now you multiply with another cosine omega CT. That's why you have a cosine square omega CT. Am I right? Okay. This picture or this diagram shows you need to pass through this YT by a low pass filter. Then you can get the YTT. This YTT is supposed to be the estimation of the original message XT. Okay, estimation only. Okay, may not be exactly the same. Why? And why this can be applied to both of these schemes? How we can explain this from the mathematical perspective? That means how we can use the derivation to show this demodulation process. Okay, let's assume that the gain of this low pass filter is just unit, that means it's 1, okay, to simplify the derivation. And the original message, xt over here, right? Xt over here has a bandwidth B hertz. Okay, because later we need to determine the cutoff frequency for this low pass filter. Remember? Yeah, when we design low pass filter, we need to be clear about the rolling off rate, cutoff frequency, right? Of course, the design starting from the low pass prototype. Okay, then you need to map in the parameters or transform the parameters. Okay, mathematically we can see this. All right, we have AM PSP signal, which is XCT. According to the diagram just now, we have XCT multiplied with a local oscillator. Okay, so we have AC times square 1 plus mu XCT cosine omega CT, which is the XCT, right? Then multiply with ALO cosine omega CT. ALO is constant, just put it here. And because we have 2 omega CT now, multiply together, we have a square over here. Alright? Next step is another trick. We need to make use of this trigonometric identity. Cosine square alpha equals to 1 plus cosine 2 alpha divided by 2. Cosine square alpha. Okay, we need to make use of this trigonometry identity. Okay, so omega CT is alpha now. So we have 1 plus, okay, just forget about this part and this part, all right? We just look at cosine square omega CT. Cosine square omega CT equals to 1 plus cosine 2 omega CT divided by 2, which is exactly the trigonometry identity over here. Just replace alpha by omega CT, right? So we expand this one. Okay, you collect these two over here. We have 1 plus mu xt multiplied with 1 plus cosine 2 omega CT here. Okay, further expand it, I have this constant term. I have this mu xt times a constant, all right? And also I have this term. Why I saw it like this? Why I didn't expand this one? There's some reason. Okay, first, what's this? Constant term, right? Constant term is DC component. What's this one? It's the signal proportional to the message, right? Because AC, ALO, mu are constant. So it must be some signal proportional to our message. So if XT is a voice signal, this one maybe is some same voice signal, maybe louder or weaker or softer compared to this one. Depends the value here. Whether this one is greater than 1 or less than 1, right? If you want to recover the original one, you can use amplifier to amplify this one or attenuate this one. So you got the same XT. Okay? How about this one? What's this? Can you recognize what's this? Can you recognize this? What's the expression for this one? Let's say AC times ALO divided by 2 is AC prime. Okay, AC prime multiplied with 1 plus mu xt times cosine 2 omega ct. Sound very familiar, right? What's this? It's another AM DSP modulation signal, right? But this time, the carrier amplitude becomes AC times ALO divided by 2, and the carrier frequency becomes 2 omega c. Okay? Okay, so what's the meaning of this? What's the meaning of this? So the envelope signal is this one. It will multiply with constant, so constant doesn't matter, all right? But this time, because it's going to multiply with the 2 omega ct, so the spectrum of this signal is going to shift to a high frequency band to center at 2 Fc, right? Or 2 omega c. Am I right? Because generally for AM DSP, if the carrier signal is omega c, so the spectrum of the envelope is going to shift to a place center at Fc. But this time, because it's 2 omega c, so it's going to shift to a position center at 2 omega c or 2 Fc. Right? And the other question is like this. Okay, I got a YT equals to this one. Mathematically, I can see that. Okay, I just need this one. I don't want this one. I don't want this one because this one not the message. Right? I just want to recover my message. Okay, mathematically is very clear. But when we implement it, how do we separate them? How you can separate this one from our message? How you can separate this one from our message? We don't know. We don't know. Right? Okay. First one, look at this. Another AM DSP modulation signal here. This signal is located at a frequency center at Fc. Its bandwidth is, what is bandwidth for the signal? For the subterm here. We have an assumption that the message signal is bandwidth B, right? Right? Okay, so can you tell me what's the bandwidth for this signal? 2B, yes, very good. Now, can you tell me what's the bandwidth, what's the frequency range for this signal? Should be 2Fc minus B to 2Fc plus B. Am I right? We're going to shift this one to a very high frequency band, right? Okay, so this is center frequency 2Fc. This is 2Fc plus B. This point is 2Fc minus B. Correct? So the range of this frequency is 2Fc minus B to 2Fc plus B. Frequency range, right? And we know that the carrier frequency Fc, this point, is much greater than B. In other words, this portion is very far from the baseband signal. Okay, so now my baseband signal is over here. Now, can you tell me how I can separate these two signals? High pass. I heard high pass just now. Low pass. Anyone want to use a band pass? So you have used all three types. Must be one of them must be correct, right? Because our useful message is located in a low frequency band, right? Low frequency band. So we should use a low pass filter to retain this portion and reject the high frequency component. Okay? Yeah. So with a low pass filter, with its cutoff frequency within a range from B. Okay, why is B? Because the original message is bandwidth is B, right? Okay, so from B to this point, so any low pass filter is cutoff frequency within this range can reject this component. and retain this component, right? Yeah, so we need to apply a low pass. That's why in the previous one, you see a low pass filter. And its cutoff frequency must be within the range of from B to 2fc minus B. Okay, any frequency within this range, you can choose as a cutoff frequency. Okay. Okay. One question. You tell me the original message signal, its bandwidth is B. Okay, no problem. But now, I'm not looking at the original message. I'm looking at this one. So can you tell me what's the bandwidth for this one? Is still B or B times AC times AL divided by 2 times V? It's still B, right? Yes. Because this is just a constant term. A constant time signal, it won't change its bandwidth. You only change its amplitude. Okay? Yeah, good. So we are finished, right? We can recover our message, but not yet for A and DSP. Why? Because we have first term yet. We haven't dealt with the first term, right? So first term is we know that first term is constant and it's a DC component. All right. To reject this DC component, what do we need? A DC blocker, right? DC blocker. So what is a DC blocker? What's a DC blocker? What kind of component can reject the DC component? Sorry? Can you speak louder? Capacitor. Any other opinion? Capacitor. Yes, capacitor is one kind of DC blocker. Yeah, there are other types, of course. But if you use capacitor, you have some loss on this component as well. That means the amplitude will reduce. Yeah. There's some DC blocker. They can retain the amplitude of this one, but reject the DC component. Okay. All right. So this is for DC AM DSP. Then how about AM DSP SC? Okay, we use a similar approach. Okay. AM DSP SC modulated signal multiply the local oscillator signal. All right. Then we multiply them together. Because XCT in this case is just simply AC XT times cosine omega CT, right? Now we have another omega CT and ALO, so we have this one. Again, we have a cosine square term. Okay, cosine square term, we use the same trick. Use the same trick, so we have this one. Okay, we have this one. Then we expand it, have this two terms over here. The first term is proportional to the message. Second term, what's this? What's the second term here? It's another AM DSP SC modulated signal, right? But this time, similarly, the carrier frequency becomes 2 omega CT. Alright? Yeah. So, we use the same approach like AM DSP. We use a low pass filter to reject this one. What's left behind is just this signal. Okay, this time we don't need a DC blocker because there's no DC at all. Alright, there's no DC at all. Okay. But this one, because the factor, the constant factor here, sometimes the voice signal becomes softer. Okay, so you may need some amplifier. Alright. Second one is the color frequency for low pass filter. Similarly, like I showed just now here, this signal, its bandwidth is from, its frequency range is from F2FC minus B to 2FC plus B, right? Okay, this one is frequency range is from 0 to B, Okay, so I need to choose a cutoff frequency for the low pass filter within a range from B to 2fc minus B. Any frequency in this range can be used as a cutoff frequency. But it doesn't mean that you can choose, in the end, you can choose arbitrary frequency in this range because there's some other constraint we haven't specified yet. Okay, theoretically, if just given this condition, you can choose arbitrary in this range. Okay, arbitrary frequency in this range. So you can, between B and omega C divided by pi minus B, this is 2fc, right? This is 2fc. Okay? So with this, we can do the demodulation for AM DSP and AM DSP SC. Okay? Okay, let's see an example. Let's see an example. The modulated signal, as previous tone modulation example, okay, previous tone modulation, remember? Yeah. The message is with 5 kHz, amplitude is 1, right? If you look at a previous single tone modulation example, message is a sinusoid with frequency 5 kHz, amplitude 1, the carrier signal with amplitude 2, frequency 100 kHz, right? Then for AM DSP, mu is equal to 0.5. Alright? So in this case, assume at the receiver side, local oscillator gain is 1, AL equals to 1. And the low pass filter gain is also 1. Then illustrate how two signals are demodulated by coherent detection. That means AM DSP and AM DSP SC. How these two signals are demodulated. Okay, we know that the carrier frequency is 100 kHz, message is 5 kHz. All right, let's assume at the receiver end or the receive side we have the same frequency, same phase local oscillator. Okay, then keep in mind that this actually in the practical case is very hard to achieve. Okay, so for AM DSP, the signal is like this. Okay, this is the message. This is carrier. Carrier amplitude 2, modulating depth or index 0.5. Alright? So after mixed with the local oscillator, we have 2 LO, 2 is coming from here, right? 2 LO times the envelope times cosine square omega CT. Okay, expand this one. Okay, the 2 cancel out. We have this one, alright? Then expand it further. We have 3 terms. We have 3 terms. First one is the constant term here. Second one is proportional to the message. Right? Third one is another AM DSP modulation. Okay? So we need to design a low pass filter with cutoff frequency in the range of 5K to 195K. Of course, this looks a very wide range. That means you have a lot of frequency to choose as the cutoff frequency. But practical case, it may not be like this because there are some other constraints. Okay, like the same frequency band may be used by other users. That means the other users already inject some energy in the frequency band from 5K to 195K. Okay, so you cannot choose arbitrary cutoff frequency. Otherwise, the signal from other users may come into user case, becomes interference to you. All right. Okay, so after we reject this one, what we left is just this 2 terms. All right, this 2 terms. First one is a constant. We can block it by using the DC blocker. Second one is proportional to the message. All right. Okay, how about the second one? AM DSP SC. And the modulated signal is this one, 2 times cosine omega CT carrier multiplied with the message cosine omega MT. Okay, this is the AM DSP SC modulated signal. Can you derive what is the YT in this case? After the mixer at the receiver side, what's the signal? What's the signal after the mixer? At the receiver end? Assume perfect synchronization. That means the local oscillator it has the same frequency and phase as the transmitter oscillator. Okay? Please try to solve this one. Okay, have you solved it? All right, we have AM DSP modulated signal XCT multiplied with local oscillator, right? This XCT actually is the message signal multiplied with the carrier signal. The carrier signal actually is 2 here, right? Then local oscillator. Okay, solve it. We have 2 times ALO cosine omega t multiplied with cosine square omega ct. Okay, this cosine square omega ct can be written like this. Okay, using trigonometry identity. Then those 2 is going to cancel out with this 2, and ALO equals to 1, given condition, right? So what we left is just this one. Message signal multiplied with the term in the bracket, which is 1 plus cosine 2 omega ct. Okay. Then expand it. This term corresponding to message. This term corresponding to another AM DSP SC modulation, which means that a spectrum should be located at a very high frequency band. So we can use a low pass filter to reject this term and obtain this term. Okay, this low pass filter is cutoff frequency must greater than omega n, less than 2 omega c minus omega n. Or in other words, its cutoff frequency must greater than Fn, if you represent using a cyclic frequency, must greater than Fn and less than 2Fc minus Fn. Okay, so from here you can see we can demodulate the signal in a synchrotron case. Okay, any questions? Any questions? Sorry? Okay, speak louder. ALO. This one, because AL equals to 1. Yeah, we have assumption that AL equals to 1. Right? Of course, it's just a constant. No matter what's the value, it's constant. Okay? All right. Yeah.
Can you explain this again one more time?
Sorry?
Can you explain the whole thing one more time again?
This one?
Yeah.
Okay. We have the signal after the mixer, right? And recipient, which is represented by YT. So mathematically, it should be the AM DSP modulated signal, AM DSP SC modulated signal, XCT, multiplied with the local oscillator signal. Right? Okay? So this is the expression for the XCT according to what we learned from the AM DSP SC. Okay? Synchrotron case, right? Synchrotron case. Okay, so we solve this one. We have 2 cosine omega ct here and here. Multiplying together, we have a cosine omega ct, right? Also, we have 2 times ALO cosine omega mt here, right? So that's why we have this term over here. Now, we expand this cosine square omega ct using trigonometry identity. We have this one. Am I right? Am I right? Okay, so this 2 cancel out with this 2 here in the denominator. What we left is ALO cosine omega mt multiplied with this summation term. And consider that ALO equals to 1, right? So don't need to consider ALO anymore because it's equal to 1. So what's left is just this one, cosine omega mt multiplied with this summation term, which is from the numerator of this factor here. Okay? Now we expand this product. We have a cosine omega mt plus cosine omega mt multiplied with this one. Right? So we know that this is a low frequency signal, a message signal, multiplied with a high frequency signal, carrier signal. So it's going to be another DSP SC modulated signal, right? Which is supposed to be located at a high frequency end. This is a baseband signal or message. So I can use a low pass filter to reject this component and retain this one. That's how we do the demodulation, recovering the message. Okay? Yeah.
You see, the low pass filter gain is 1, right? Why did we write 2?
Oh, I haven't talked about the gain here.
Oh.
I haven't talked about because you're going to pass this everything here through the low pass filter. Then the gain and for the pass band is going to 1, and for this band, because it's going to remove it, right? So the gain for this term is going to 0. One left behind is just this one, the message. Right? Yeah. So everything looks very beautiful, right? Perfect recovery. But since that, in the reality case, we have noise, we have attenuation, because the RF signal propagates from the transmitter to the receiver, definitely there was some attenuation. So the received signal XCT here at the demodulator cannot be exactly same because same amplitude here. We have made assumption here. There's no attenuation at all. That's first one. Second one, we never consider any noise here. Right? We don't have any noise term here. So in practical case, we have this one plus a noise term. So this noise term is going to create some noisy signals in your earphone or your speaker. Right? One more thing is about the local oscillator here. So just imagine we don't have this perfect synchronization. Let's say we have a non-zero phase here. So what is going to happen? We cannot put square then. Right? Cannot be square. So what happened here? Then here is going to be half of cosine 2 omega ct plus cosine theta. So what's the consequence of this? What's the consequence of this? This term is going to replace by this one. If the synchronization are not perfect. I haven't talked about unsynchronization because the frequency yet. I'm talking about phase difference. I haven't talked about frequency difference yet. Right? So if this is like this one, what's going to happen? This term multiplied with this one, high frequency component. Okay, so we can remove it. But the recovered signal is going to be cosine omega t, omega mt, multiplied with this cosine theta now. Right? And consider that this theta generally can be a random variable. That means it will change from time to time. So that's why sometimes when you listen to the radio station, the voice signal or the intensity of the signal sometimes becomes very high and sometimes becomes soft. Do you have a similar experience? When you listen to the radio, the volume actually is not constant. Sometimes it becomes very high, sometimes it becomes soft. Right? That's why. Because this synchronization is not perfect. There's a non-zero phase, and this non-zero phase generally is a time function as well. But it's just this time function, the phase change very slowly. So that's why you hear the volume sometimes become very loud. Then you turn them lower. After some time it becomes even lower. It's quite annoying in this case. It's quite annoying. Right? Then how about we have a frequency variance here. That means in the practical case, okay, let's look at a simple case first, all right? Instead have this one. I have this cosine omega c plus delta omega t. Okay, delta omega of course is a very small frequency. Okay, it's a very small term compared with omega c. Then what happened? What happened? Okay, just ignore this. Okay, we ignore this one. Then of course we don't have this one anymore. what is going to happen here is cosine 2 omega c plus delta omega t, then plus cosine delta omega t. Yeah. Okay, this one multiplied with message becomes another DSB-SC modulated signal, high frequency band. Although the carrier frequency is not a constant, but we don't need to worry because we can reject it using a low pass filter. What's left is this term multiplied with the message here. So what's the consequence of this one? What's the consequence of this one? Your message now multiplied with this term. What happens? You are modulating your message, right? If this is view this one as a carrier frequency, that omega as the carrier frequency, now actually you are modulating your little message again. But this time, because delta omega is a very small frequency, although you modulate it, you still can tell the voice. You still can tell the voice information. It just you will hear some whistle inside. This whistle is due to this term. It's due to this term. Because what you hear is that this one multiplied this one. So this is all. It is very common when you listen to the radio station, right? Okay, there are some non-perfect effects here. Okay, with this I finish my part for this module. Okay. So we have talked about the application of signals in computing system. Okay. So the first important thing is that we need to know how to do this simple Fourier transform. Okay, we have shown you some examples during the first chapter, right? Remember, we need to know those are typical Fourier transform pair. Then you can derive the Fourier transform for other signals. We now come a very intensive computation. You don't need to do the integration at all, actually. So you can do the Fourier transform in this way. Right? Then we say that modulation and filtering are two important topics in communication. We can apply what we learned in the signals to discuss modulation and filtering. Okay, so we learn about how to design a Butterworth filter, of course passive Butterworth filter, right? So for passive Butterworth filter, we always study from the low pass prototype. No matter in the end, the filter you want to design is a low pass, band pass, or high pass. You always study from the low pass prototype. Okay, but low pass prototype means that the color frequency for low pass prototype is 1 radians per second, and the matching impedance is 1 ohm. Okay? Then we can come up with the two configurations, pi type and p type. Alright? Then we can find out, once we determine the order n, so how to determine order n? We need to solve an inequality, define the minimum integer number n, satisfy the inequality. Because we know that in a rolling off region, a low pass prototype rolling off at 20 times n dB per decade. To solve this inequality, we can find out the order of the filter, right? Then once we solve the n, we can determine parameter from G1 all the way to Gn. Depends the configuration you're going to use. You can interpret it into capacitor or the value for capacitor or the value for inductor. Right? Then after that, you can transform the parameters in the low pass prototype to a particle filter, no matter it's a high pass, band pass, or low pass. Okay? You don't need to memorize the table. The table is given. Don't worry about it. Okay? Don't worry about it. For both the table for parameter G and the transform, don't worry about this. You need to know how to use it. That's the most important thing. And what's the meaning of these parameters in the table? Okay, that's the most important thing. Right? Then in the second chapter, we're talking about how to do the modulation. One example is F2 modulation, and we need to know that why we need to do the modulation. There are two reasons at least. Actually, there are more than two reasons. I just mentioned two reasons in the lecture, all right? One is because the antenna size. Remember, we have example. To carry a 75 meters antenna, right? Yeah. Then another one is try to avoid spectrum overlap. That's why we need the modulation. And then we come up with the two AM modulation scheme, AM DSP and AM DSP SC. Why we need to talk about these two is because these two are very typical. These two are very typical modulation schemes. Each one of them has disadvantage and advantage. Okay, we need to know how to analyze the spectrum for those two schemes. What happens after modulation? What happens to the spectrum? Okay. Also, we need to know for these two schemes what expression, and especially for the single tone case, what is the expression? All right. Then after we know that modulation, next topic is about demodulation. Okay, demodulation. We need to use the multiplier. We need to use the low-pass filter, and sometimes we need the DC blocker. Mathematically, how to express them and how to derive from a modulated signal all the way to the message signal or the recovered signal. You need to familiar with this derivation. The only trick here is just this one. Cosine square omega ct equals to 1 plus cosine 2 omega ct divided by 2. That's the only trick here. Okay, I'm not going to test you about this non-perfect case, non-zero phase, and not exactly frequency. All right, I'm not going to test you about this. The reason why I mentioned this is just mapping this to your daily experience when you listen to the radio. Why you can hear, why the volume keep changing, and why you can listen to the whistles in the radio receiver. Okay. Okay, with this I finish my part, but I'm going to see you guys again next week. Okay, during the lab session. Yeah. There's no lecture for next week until the Monday evening during the recess week. All right. Then after the recess week quiz, then we for part 1 finish. Okay. Then the part 2 was starting from week 7. Of course, take over by another professor. In the meantime, if you want to discuss me with FYP project, you can email me. Yeah. All right. That probably haven't been finished yet. Yeah. I will change the.